0. Finally, gentlemen, some applications of integration. Here we want to draw a sketch of that curve, which is in fairly convenient form, and find the area enclosed by it and the x-axis. Well, it's in convenient form at the moment because we can easily identify the x-intercepts of this curve. The x-intercepts are where x is equal to 0, where x is equal to 1, and where x is equal to -1. That's pretty well all you need to know about this curve. So if that is the case, let's put a -1 there, a 0 there and a 1 there. We notice that if we expand the x terms, that times that, we get x cubed, which is positive, and it means our curve is going to start from down there and end up eventually up here, very positive. Okay? So really our curve, and this is all we need to indicate, is going to look like that. So what's to be found is the area between here and here. Now we know that when we evaluate an integral and the area is under the x-axis, it evaluates to a negative, but we don't have negative areas. So what we've got to do is take the absolute value of the integral between 1 and 0, which will give us a positive value, and add it to the area found here. But of course, before we can do the integration, what we need to do is expand out our expression. Okay? Now, the quick-witted amongst you would notice that if we ignore that x, what we have is a difference of 2 squares. That's going to make our expansion easier. So we can say that y is equal to, let's forget about that x for the moment, x squared minus 1. That's our difference of 2 squares there. And so expanding, we can say y is equal to x cubed minus x. Well, that's going to be fairly straightforward to integrate. We've just got to be careful with our intervals. Firstly, our area is going to be given by this. As we can, well, this is showing us that our area here is negative. We don't have negative areas, of course. So what we need is the absolute value of this integral between 1 and 0. And that integral is right there. Well, the expression is right there. Okay, and dx. And to that, we need to add, it's going to be positive, so we don't need to worry about the absolute value. Our interval here is 0 to -1, upper limit of 0, lower limit of -1, and it's the same expression we are integrating. Okay, so that should give us our area. Alright, so let's do the integration. Therefore, the area is equal to, using square brackets, we get x to the power of 4 over 4 minus x squared on 2. So x to the power of 4 on 4 minus x squared, absolute value, just remember, over 2. Our limits were 1 and 0, absolute value, and there, and here we get to recycle our information. The interval is obviously going to be the same, but the limits are different. X squared on 2, close up that bracket, and our limits here were 0 and -1. Alright, so what do we get here? Well, 1's not a bad number and 0's an even better number to be substituting in. What we're going to end up with is anything, 1 raised to the power of anything is 1. So we've got a quarter minus a half, haven't we? So it's the absolute value though, a quarter minus a half. Absolute value thereof. Plus, oh, and by the way, we're going to have 0 take 0, so you can forget about that. I said plus, I meant, yes, that's right, plus. I was getting in a bit of a tangle there. Alright, 0 minus 0 is 0, of course, and then we've got a minus this. Be careful of signs, very much so here. So I'm going to put in the fact, so I don't end up in too much of a tangle, that when I substitute 0 in, I get 0, and then I'm going to minus. Now, -1 raised to a positive power will be +1, so it's minus, I'm going to put that in square brackets and this in rounded brackets, so it's positive a quarter. Now, -1 squared is 1, so it's minus a half. Be very careful with these signs. They can be deadly. And square brackets there. Okay, so I'm going to have to go up here, I feel, to continue my working out. What do I end up with? Okay, it is the absolute, well, a quarter minus a half is a quarter. Negative a quarter, but it's absolute value, so it's positive a quarter. So that's the area, in fact, between here and here, isn't it? And what have we got here? Plus, let's be a bit careful. Okay, it's the same sort of thing here. Quarter minus a half is negative a quarter, but I'm subtracting negative a quarter, so it's going to be positive 1/4. It seems that the areas are the same size. Okay, and that will equal a half, but that's not good enough. I need to indicate that we are dealing with squared units. Therefore, area equals a half of a square unit. Okay, looking at our next example. The shape formed by the area between y equals x and y equals x squared is rotated around the x-axis. What volume has the resulting solid? So we need to know something about what these what straight line and curve looks like. Fortunately, they're reasonably routine. So, firstly, our straight line y equals x, well, we know it's going to pass through the origin because there's no constant term there, is there? And we know that this is the stock standard parabola. So they intersect like as follows. And to find where they do intersect, well, it's fairly obvious that they intersect where x is equal to 0. What's not so obvious is what this point is here. And so when we want to find that out, what we do is we let one equation equal the other. So, intersection points. And as long as they're both equal to y, or fx, what you can do is say, let that equal that. Okay? Therefore, let x equal x squared. Okay, now let's rearrange a bit so that we get this. And how we would solve that is not by common sense but by factorising. X bracket x minus 1 equals 0. And the null factor theorem is telling us therefore that x equals 0 or x equals 1. What we're doing is we're saying, well, you know, x equals 0 or x minus 1 equals 0, and when we solve that we get x equals 1. Okay, so that's the area we're finding. Now, what are we doing here? Well, we're rotating around the x-axis. This funny shape here is being rotated around the x-axis. When we rotate a shape around the x-axis, we say its volume is given by pi. We're going to have some limits or other. Let's call them b and a. In this case, they'll clearly be 1 and 0. What we do is we square the function or the equation and we find the derivative in respect of x in this case, because we're revolving around the x-axis. So what do we do? Well, don't forget that we've got a line, which is the upper function, and the parabola, which is the lower section of what's being rotated around the x-axis. So what we need to do is say this: the volume is equal to pi. Our limits are 1 and 0. Now let's be careful here. The upper was a straight line, so it's x minus x squared, but you've got to square all of that. Okay? Remember, it's really mimicking pi r squared because you're summing circular discs all the time. And dx. Alright. Now we've got a perfect square here. Volume equals pi. We've got to expand this out before we can do anything. We can't use the chain rule because it's not a linear factor in there. So, but what we can do is expand it out to get first term squared plus, or in this case minus, twice the product of the inside terms. Now be careful, that's going to be twice the product is x times x squared, but that's x cubed. and plus the last term squared, so x to the power of 4 dx, like so. And now we're ready to integrate. It's fairly routine. Don't forget your pi out the front there. So the volume is equal to, integrating now, pi, x cubed on 3 minus 2x to the power of 4 on 4. So I'm going to simplify that. The 2 can go out and I'll divide the bottom by 2. So it'll be x to the power of 4 on 2 plus x to the power of 5 on, the new index is 5. And my limits here are 1 and 0. So the volume, this should not be too difficult because we're dealing with ones and zeros. 1 raised to any of the power is 1. So we've got a third minus a half, whoops, too quick, plus a fifth, 1/5. And I don't need square brackets, I should in fact use round brackets. The 0 is going to yield 0 minus 0 minus 0, so it doesn't really count. Now what I need here is a common factor for 3, 2 and 5. I think the best I can do is probably 30, so the volume is equal to pi, times that by 10, because I'm timesing 3 by 10 to get to 30. I've got 10 minus 15 plus, times it by 6, like so, and V equals pi. Alright, what I've got, so 16 minus 15 is 1, so I've got times 1 on 30. That looks very untidy. So what I've got is volume equals pi on 30 units cubed because it is a volume. Thank you very much. We'll stop there.